right, good morning, everybody. And good morning also to the hundreds of thousands of people who are going to be watching this in the recording online. So hello to that camera up there. For everybody down there, every now and again I will wave up there. And for everybody on the camera up there, every now and again I will speak to the people in the room. So I hope that doesn't confuse anybody. My name is John. I'm from the NCC in the UK. I rejoice in the job title of Senior Chief Engineer. And I lead engineering across our civilian portfolio. So if it doesn't involve blowing people up, then it's in some way my problem. I'm going to talk to you a little bit today about how we can maybe address some of the challenges in designing sustainable composites and why we might want to address those challenges, how we can really make the next steps forward. It was really interesting in a panel session yesterday, discussing some of the reasons why life cycle analysis is limited at the moment, some of the challenges in really getting under the hood of how life cycle analysis works. And I'm going to try and work some of these into this talk, even though I had to give the slides a month ago. So let's talk about why life cycle analysis, and there will be a little bit of audience participation here. And so I hope you're all awake, and I hope you're all ready to answer one or two questions. Or actually, just put your hands up. So I'm going to tell you a story of two aircraft engine companies. Both of them offer what they call power by the hour. So both of these, the aircraft engine company is not selling an engine, they're selling the ability to use the engine. And they follow two quite different approaches to this. One of them offers time on wing. So one of them is trying to maximize the amount of time that each engine is spending on the aircraft. They want to make the minimum number. They want to do as little repair as humanly possible. So they design their product to be as durable as possible. Because they've designed it to be as durable as possible, maybe they've lost a little bit of performance, not a lot, but a little bit. And the other one is really tolerating no disruption. The difference here really is that this one, they're attempting to achieve very high durability, which means when things do go wrong, they haven't expected it. And so there's some disruption in service when the unexpected does inevitably happen. In this one, they're targeting what I'm calling a no disruption model. They've scheduled a lot of maintenance. We're servicing our car very regularly. So we're planning for this. We've got inventory, we've got stock ready to go to replace parts that are wearing out as they wear out. Because we're not targeting quite so much durability, we've got a little bit higher performance here. Maybe our blades are a little bit thinner. So maybe this has slightly higher performance, but we've got much higher inventory. We've got a lot more parts around us because we're replacing a lot more. So the costs of this, the direct costs of this approach are maybe higher. Who's done better? Which business model is better? Really, really strong, very durable, but surprising when it goes wrong. Or we expect it to go wrong, and we have a lot of money invested in having spare parts available. Who's going to vote time on wing? Who's going to vote no disruption? Ah, interesting. Okay. What about wind turbine? So here we're trying to maximize our asset earning potential. We're trying to maximize basically the amount of time that the wind turbine is generating power. And again, we've got a similar choice to make here. We've got superleggera, we've got the super light. We've got very light components. They have lower impact. Because they're light, we've not embodied much material. There's a lower embodied carbon here. We've not used so much materials. We've not used so much energy for the processing. It costs less because we've used less material and less processing. But maybe, just maybe, there's higher operating costs because the thing is not quite so durable. Or we've got the opposite of the superleggera, the super light, and we've got the tank. So this one is very durable. We've embodied a lot of material and a lot of processing, so the impacts are higher, the capex is higher, so it costs more to put these in place, but maybe it costs less, maybe significantly less, to operate them because they're more durable. Again, who's going for superleggera? And don't say you're going for this just because you like the word. Who's going for the super light? Who's going for the tank? Interesting. Now, when you've been making those choices, you've just been making judgments. You have no calculations on which to base this. What would it look like if you did have calculations on which to base these judgments? well, it would look something like this. So this is something that we did. So this is for a wind turbine blade. So this is looking at the global warming potential per megawatt hour for different amounts of usable life. And this is looking at trying to understand and answer the question, if I can get more life out of my wind turbine blade, but only by embodying more carbon, only by using more materials and using more energy, have I actually done a good thing, or have I not done a good thing? And the answer is, for a wind turbine blade, the trade is about 20% of manufacturing impacts. So we're not talking about life, like end of life or anything here, just the embodied carbon when we made the thing. You can trade about 20% more manufacturing impact for about 5 years of life. So that's a pretty good trade. So you probably don't need 20% more blade to get 5 years of life. So this trade probably works. I would have liked to have shown you another slide, but I decided I didn't have time for an aircraft engine. It totally doesn't work. So the trade is not a good trade for aircraft engines. But just the point here is that just getting to these numbers to underpin the judgments that you all made in the room, and I hope people followed along on the video as well, this calculation is a very difficult calculation to perform. And so we have to judge the best approach when companies are deciding how they're going to approach, how they're going to build a business model for in-service products in service. They're relying an awful lot on judgment because we lack effective ways to make these kind of calculations. We typically estimate durability, and this is one of the main things that the D-STANDART project is looking at, durability. We typically estimate durability just before market entry. So we've done all of our design, and then just before we put something into service, we do a fatigue calculation. And maybe we look at corrosion, but these are all difficult offline assessments. And they're done just before market entry. They're probably done once unless something goes badly wrong in service. And we rarely iterate based on that result. We hope that we're going to get the life that we want. We don't know that. And it's only if there's a real disaster that we'll make a change in design. We quite often at the moment, we don't estimate life cycle costs and impacts. Sometimes we do, oftentimes we don't. And even when we do, again, like durability, it's done just before market entry and it's done once. Most companies, although very few of them will admit it, are using revenue service to learn about their products. And by that I mean it's a very important source of learning about how your products behave in service is to watch your warranty returns come in and listen to how angry your customers are with you. This is a very common way of learning about life cycle analysis, of learning about your life cycle just by watching it happen. All of this means that by the time we actually know anything about our products, it's far too late to change. Well, it's not too late to change, but the cost of change is very, very high because we would need to make new tools. We'd need to roll out things in the fleet. We'd need to retire old product from the fleet and so on. I stole this idea shamelessly from Rolls-Royce, and I hope that there's nobody from Rolls-Royce in the audience. I did ask. It's okay. This is Tony Bell from Rolls-Royce's services value equation. We want to maximize services value, which means we want to maximize revenue from our service operation. So this is power by the hour. This is when we're selling the use of a turbine of some kind. We want to maximize that revenue. We want to minimize the recurring costs, so number of service interventions and the cost per intervention multiplied together, recurring costs. And we also want to minimize fixed costs. Okay, fine, no problem. How hard is that? Nice, simple equation, right? But this means doing life cycle analysis, which looks like that. That's a life cycle inventory for a wind turbine blade, for a spar of a wind turbine blade. Not even a whole blade, and the blade is not even the whole turbine. That's part of the life cycle inventory. So if we zoom in, so for each bit, we're looking at what equipment we're using. We're looking at how much electricity that's using. We're looking at how much waste that process is generating. What's happening to that waste? Oh, for the guy that's laying this up, how many consumables is he using? How many pairs of gloves is he using? We've got to record all this data. It's a nightmare. We've got to think about the fuel that's used to transport the materials to our facility. And this is what came out of our panel discussion yesterday, is that there is physics underpinning life cycle analysis. There are real physical processes happening here, but they're very, very deeply buried. They're under many layers of complexity. And so if you want to figure out a detailed life cycle analysis, and you don't just want one that you can use numbers to make any story that you want, then you have to go and uncover that physics. It's very complicated. So what can we do about this? Well, if you're doing a life cycle analysis to the ISO standard, there is an option to do a simplified LCA. Well, that sounds great, right? Simplified LCA. Well, I just told you that LCA was too complicated, so you want a simple one. Well, simplified LCA to the current ISO standard is based on generic correlations. It's based on things like, well, a kilogram of carbon fiber is worth 300 kilograms of CO2. And that's grossly oversimplified, because that varies hugely depending on how it's made, where it's made, what the energy mix is, what the processing was. And so when you average up these generic correlations, we don't need to know very much about the design, but we get very inaccurate results. Are they even useful? Possibly not. The other option, the only other option today, is to do what we call variable input, which is what we talked about before, which is you need to know a huge amount about the design. You need to pick down through all of the levels of detail to figure out exactly what is going on in all of the processing, measure out everything, and you get, once you've done all of that, you get beautifully accurate results, but you're never going to do it. Or if you do it, you're going to do it once at the very end of your design and never ever do it again because it was so painful. You can't use this as a design tool. Now, what we noticed when we were making things for D-STANDART, we really want to address this problem and try to build tools that enable us to bring life cycle assessments of ecological impact and cost into design iteration. And we noticed, so this is the cell power, which is drawn by our big robot when we're making AFP blades. So this is our big AFP robot. And you can notice there are several different stages here. So we could worry about the individual detail of all of these. These peaks are a laser chiller switching on and off. Or we could actually, there are some sub-processes happening here. This is the electrical load which is required just to run the cell. This is the electrical load which is required to run the cell with the robot laying up material. And this is the electrical draw which is required to move the whole robot from one place to another. So here we can see that somewhere in between the very basic generic correlation, also the very basic generic number for carbon fiber, and the incredibly detailed number for the laser and the moving the robot head and the everything, there's another level in between, which is based on sub-processes. So how can we get to these sub-processes? Because these would be really useful if we could figure out how we can get an understanding of how sub-processes are building together to produce a component. Then we can do this. We don't need to know loads about the design. We don't need to go right down into fundamental physics, but we can still get pretty accurate results, usefully accurate results. All models are wrong. Some models are useful. And the way that, so the conceptualization that we have in D-STANDART for this is to think about parts as collections of features and to make the assumption that useful information about engineering and production sub-processes exists at the feature level. So we've got, for example, in this semi-complicated component, we've got ramp features, we've got flat areas, we've got steering regions, we've got corners, we've got thick sections, we could have holes, for example. So if you think about the composite parts that you know about, that you work with on a day-to-day basis, you can, in your mind, you can decompose these into collections of particular features. Now, what can we do with features? Well, features are very useful. We start with basic geometry. We start with basic understanding of our design on the left-hand side there. What it looks like, the overall geometry, and where the plies are, the layup. And we can decompose that into features, as I've just described. Against each of these features, we can have rule sets. And by a rule set, you hear a lot about data-driven engineering, where people are using simulation and brute force computation to try to understand how things work. I think humans already understand quite a lot about engineering processes. And so there's a huge amount of knowledge which is already in experts' minds about how, like, what kind of layup works well to go over a flange, for example. How you can make a hole pattern work. What kind of drill works best to drill that kind of hole. What makes things inspectable or not. So against each of these features, it is possible to define rules. What works and what doesn't. We haven't done any simulation here necessarily. But we can work these out through experience, and we can get the information out of an expert's head, codify it into a machine-readable rule, and hang that off the feature. And then we can use those rule sets to define business impact. A simple example here being, we know that curvature, how curved a part is, affects how inspectable it is, and more importantly, how long it takes and how much it costs to inspect the part, because of the width of the phased array probe that you need to use to get over that curvature. So it's just a simple example there of the kinds of inference, the useful business knowledge that we can put against different features and different attributes of different features without actually doing it necessarily any simulation at all. And we can do this with LCA as well. So once we've got down to these design features, we can build understanding. We can build rule sets based on our understanding of typically that kind of feature requires 100 millimeters of AFP runoff. That kind of feature normally produces about 10% waste. That kind of feature probably means we're going to need to move the whole robot from there to there. So that means 8 kilowatts of power, not 5 kilowatts of power. You can start to see how this builds up into a usefully accurate life cycle assessment. So how does this help? It gives us better data. By not sitting at too high a level, where we just go, carbon fiber is worth 300 kilograms per kilogram of CO2, and not trying to go to too low a level where we try to uncover the fundamental physics which is very deeply buried. But we actually try to generate useful insight at a middle level based on engineering sub-processes and design features. We can get usefully good estimates of the life cycle, both in terms of the ecological impact of the life cycle and in terms of the cost impact across the life cycle. And a fundamental underpinning of this is the idea that good estimates of how products behave through their life means good decisions about design. And this is this problem with durability and life cycle being estimated once, if at all, just before the product goes into service, when all the tooling is already made, all the parts have already been ordered, and the cost of change is incredibly high. So the idea here is all about bringing durability and life cycle assessments into the early stages of design and enabling better trade studies, enabling us to better answer the question, if I can get 5 years extra life from my wind turbine, but I need to put another 40 kilograms of carbon fiber and epoxy on it, is that a good idea or is it not? Because at the moment we simply don't have the techniques, not techniques to answer that quickly, so that if the answer is no, we've still got time to go and try something else. And essentially what it boils down to is minimizing this. We go back to Tony Bell's services value equation. The total cost of service interventions across the life cycle, both recurring and non-recurring costs together. We want to minimize that and get the most value we can out of our products. I think probably 1 minute is probably not quite enough time for questions, but I'm here. The D-Standard stand is just over there. If you want to talk about any of this stuff, please come and find me. There's my email. Or if you've got any really difficult questions, Marco Narvine from NLR will be very happy to answer them for you. Thank you very much.